So this is the review for exam 1, and so remember before you do this to review some of the math skills review problems that we did for homework, and then work these problems on a separate paper. So let's do the first problem. And in the first problem we want to find the domain of this function using interval notation. So remember, for the domain of a formula, there are basically three things we need to watch out for. So the first thing is we need to watch out for if we divide by 0, so we don't want the denominator to be 0. And then the second thing is if you have any sort of even root function, in particular square root function, whatever's inside there needs to be bigger than or equal to 0. And there is a third thing which we haven't talked much about, and we won't do until we get to logarithmic functions, but when we do natural log functions, they have an inside, and whatever's on the inside we need to make sure is bigger than 0. But we're not going to do this one right now. So we just simply go through these. So for the first one, you ask yourself the question, is there a denominator? And of course you say, of course there's a denominator. It's right there. And we want to make sure that thing is never equal to 0. Otherwise we'll be in trouble. So we want to make sure x squared minus 4x minus 21 is not equal to 0. And so this is a quadratic equation, basically, and to solve a quadratic we should be able to factor it. If not, we'll have to do something else. So it's going to be x plus or minus something times x plus or minus something, and we don't want that to be equal to 0. And the something comes from the 21, so when I think of 21, I think of its most common factors, which are 7 and 3. And is there any way to add 7 or subtract 7 and 3 to get 4? And certainly there is, so I can do minus 7 and then plus 3. So this should give, when you multiply this out, this should give us this back. And so we know now that x minus 7 can't be equal to 0, right? So if you have this times that not equal to 0, then this must not be equal to 0, and this must not be equal to 0. And so we took a quadratic equation, we turned it into two separate linear equations. We add 7 to both sides. We know x cannot be equal to 7, and x cannot be equal to, we subtract 3 from both sides, so x cannot be equal to negative 3. So on my number line here, I'm going to write down negative 3, and I'm going to put a hole here, so a hole at negative 3, and I'll put a hole at 7. So it can be, so right now, I can put any number into this function except for negative 3 and 7, but there can be there's one more condition, the second one, which has a square root, so you ask yourself the question, is there a square root? And of course you say yes, because on top, you'll see there's definitely a square root there. And so you need to make sure whatever's on the inside, so what's on the inside of the square root is this x plus 5. We need to make sure x plus 5 is bigger than or equal to 0. And so we subtract 5 from both sides. And what do we get? We get x on the left is bigger than or equal to negative 5. So down here, negative 5 is to the left of 3. We'll put close bracket because it's include, and it's bigger than, so we shade in everything to the right, jump over negative 3, shade into this, jump over 7, and keep shading into the right of 7. So my domain, which can be easily read off of this number line, is negative 5 to negative 3, parenthesis, union, parenthesis, 3 to 7, parenthesis, union, parenthesis, 7 to infinity. So there's my answer. Let's take a look at the next problem. So that was domain. The next problem, what we have here is a word problem. And to do this, we want to draw a picture. And so in this picture, what do we have? It says we have 2,200 feet of fence to enclose a rectangular playground, and subdivide it into two smaller playgrounds by placing a fence parallel to one of its sides. Alright, so for my picture, I have a rectangular playground. I'm going to subdivide it into two, so I'm just going to draw this down the middle. These are supposed to be the same area, basically. And how much fence do I have? I have 2,200 feet of fence, so I'm going to write that down, 2,200 feet of fence. And we want to express the area of the playground as a function of one of its dimensions. So find a formula for the area in terms of one of its dimensions. So I'm going to call this side x. So formula for the area in terms of x. And so the bottom is x, the top is x, and then of course I'll call the sides y. And of course you have a choice. I mean, I said find the formula for the area in terms of x. You could also say find it in terms of y. It really doesn't matter. You can do it either way. And so an equation for the area, well, the area of this rectangular playground, the whole thing is just length times width, so x times y. And now I need to get rid of one of these, x or y, so that's where that 2200 is going to come into play. So 2200 is equal to the amount of fence. So, you know, you have x feet here, y feet there, x feet there, y feet there, and y feet there. So you have 2 x's plus 3 y's. And we'll solve this for, let's solve this for y. So we'll bring over the 2x, so 2200 minus 2x is equal to 3y. And then we'll divide out by 3, so we get 2200 minus 2x, all divided by 3 is equal to my y. And so I'm going to get a equal to x times what? Times what this y is. So here's y right here. And so you just copy it down. 2200 minus 2200 minus 2 times x all over 3. And so this is my formula for the area. And if you notice, it is in terms of x, so you can just leave it like that. And so the idea of a function is if you plug a value in for x, so if you plug, like, say, 10 in for x, meaning that the length of this playground is 10 feet, which is not very big, then you could get out what your area would be for that playground. A more realistic number for x might be 100 feet. And so if you plug in 100 feet, again, you plug 100 in for x and 100 for x, and then you do this multiplication, and you get out the area for the playground. So we have now written the area as a function of one of its dimensions, basically its horizontal dimension. All right, let's take a look at number 3, where we start talking about functions and change. And so let's answer these questions here. Let's find the domain and the range. So remember, for the domain, these are input values. And you notice that this arrow goes down all the way down, so it includes all these input values. We're just looking at the inputs, all the way until we get up to number 2. And I'll stop at number 2, and above number 2, there's an open parenthesis. There's an open circle, which means do not include, so it just goes up to 2 but does not include it. So my domain would be everything on the left, so negative infinity, up to 2 but don't include it. And then for my range, I look along the vertical, and you notice this goes all the way down, so everything's good down here. Good, 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 good. And it continues to go up. And it goes up right to this point. Now, to the right of the point, there's an open circle, but to the left, there's a closed circle. So I would include this point right here, which is positive 4. So my range would be from negative infinity to positive 4 and include 4. Now, x-intercepts are where you cross the x-axis, and so I'll see there's at least one. So there's one. Oh, and there's another one right here. And so the first intercept, remember this is actually over negative 2, so it's negative 2 comma 0. And the second x-intercept is at 1 comma 0. So in 1 comma 0. Now remember, these aren't intervals, these are actually points, the coordinate pairs. And then finally there's a 1 y-intercept right here, and so that's at 0 comma 2. Alright, let's delete this, erase this here, so we can start talking about increasing and decreasing. So for increasing, you're looking for when the function's going up. Now remember, you're reading it from left to right, so I'm just going to trace it going up from left to right. So I'm going up, going up. And then of course I change and start going down, but then down here I pick up again, I start going up, 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 up. So it's increasing from minus infinity, so I go all the way out here, good, 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 and increasing until I get up to negative 1. So negative 1 in parenthesis union, so it's not include, that's a parenthesis right there. And then including 1 to 2, because that's where the graph stops after 2, or at right before 2. So union 1, comma 2. And then decreasing every place else, of course, but you can just draw it if you want. So decreasing, 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 decreasing. So from -1 to +1. So we're decreasing from -1 to +1. You have relative maximums and minimums. You can see it where you change color, or you can just say, at these sort of relative, these close by maximums around it's the highest point. So that's f of -1 equal to 1, 2, 3, and 4. So it has a relative maximum at f of -1 equal to 4, and a relative minimum at f of 1. So if you look right here, it's a low point, then it turns around, so where you change color basically. So f of 1 equal to 0. All right, let's go on and take a little look at concavity here. And then we can talk about the inflection points. So for concave up, we're going to use green. And we're looking for smile. So this is definitely a frown all the way around here, and then it turns into a smile. So I'm guessing that this is probably concave up. And then to the left there, of course, it's concave down. You can draw that too. So it's all part of a frown. It's concave down. And we can put this in here. So let's do concave down first since I have this red pen out. So it's from -infinity. So it's all this stuff until you get all the way to 0. So -infinity to 0. Then after that, it becomes concave up. So when you pick it up at 0 here to the right, until you get to 2, you're concave up. So from 0 to 2. We have inflection points where you change concavity, or in this case where you change color. So since we went from red to green, we'd count that as an inflection point. So we have an inflection point at 2, 0. Now remember, that's a point and not an interval like these two things here. All right, so that completes that problem. And then the next problem, what we're going to do is we're going to find the average rate of change of a piecewise defined function. So here's our function. Notice it's defined in pieces. This piece if you're less than or equal to 2, and this piece if you're greater than 2. And what we want to do is find that average rate of change of the function from x equal -3 to x equal 4. So this is actually pretty simple. Remember the idea of average rate of change is changing the output over the change in the input, so the change in the y stuff over the change of the x stuff. We're going to go from -3 to 4, so basically the idea is always the final minus the initial, so f of 4 minus f of -3. That's a change in the output, divided by the change in the input, so the same order, 4 minus the -3. And then for f of 4, you have to decide which one you're going to plug it into. Are you going to plug it into the top or the bottom? And because 4 is not less than or equal to 2, you're going to plug it in the bottom because 4 is bigger than 2. So we'll plug it in here. And so we'll get 3 times 4 minus 5. And then minus, let's switch colors here. We want to do f of -3. So in this case, since -3 is less than or equal to, we use a top piece. And I don't like yellow. Let's use red. So we'll use the top piece. And put parentheses around it. So we have 1 minus a -3 squared in parentheses. And then that's all divided by 4 minus a negative is a positive, so 4 plus 3. And so what does that equal to? So we do the math here, and we get 12 minus 5, which is 7, minus, and then you have -3 squared, which is positive 9. 1 minus 9 is what? 1 minus 9 is -8. And that's all divided by 4 plus 3, which is 7. And so you're really adding 8 here because minus and negative is a positive. So you really have, 15 over 7 for your final answer. All right, so what does this number actually mean, though? So if you graph this function and look between -3 and 4, what you'll see is it's not decreasing, it's actually increasing. And it's increasing on average. If you go over 7, you go up 15, or you can say if you go over 1 unit, you go up 15/7 of a unit. So on average, it's increasing between -3 and +4. All right, let's see what's next. So now we're going to do the difference quotient, which is really a generalization of average rate of change. I'm going to do it with a fraction, a function that has a numerator and a denominator. And so it's real simple to do once you get the hang of it. So you can do f of x plus h minus f of x, all divided by h. And remember, a function's a rule. So this rule says basically whatever's here, you do 8 divided by it. So what you want to look at when you do this is that whatever's here, you're going to do 8 divided by it. So the first thing, f of x plus h, is 8 divided by x plus h. And then minus f of x, which is just 8 over x. And then all divided by h. And because you have fractions on top, you'd like to find a common denominator. So the idea is there's nearly no x's in common. Sometimes students will say there's an x here, but I'll say no, that's really an x plus h. So what you need to do is get an x on the bottom by itself. So you put one there. And you also put it up here. That way it's still 8 over x plus h. And then same thing here. There's not an x plus h, so you put it on bottom. But also you want to put it on top. So they're still the same thing. And now you can bring together numerators because you have a common denominator. So this is going to be equal to 8x minus 8x plus h. And then that's all divided by h. And so then that's equal to 8x. Now you're going to distribute this minus 8 through, so you can get minus 8x. Then minus a positive is a minus, so then minus 8h. All divided by h. And here's where the 8x's are going to cancel. So this 8x cancels with that 8x. And you're left with what? Negative 8h. Oh, I missed my denominator here. My bad. Let's go back and fix this. All right, right here when I brought them together, you see that? I'm missing my denominator. So easy to do. So x times x plus h. And this is still all divided by x times x plus h. X times x plus h. And so this is still divided by here x times x plus h. And that whole thing's divided by h. I saw that because I knew somehow these h's were supposed to cancel, and they weren't going to cancel like I wanted them to. So now I multiply by h over 1. Right, I'm dividing by h over 1, so I'll multiply by 1 over h. So remember, when you divide by a fraction, you multiply by its reciprocal. So I have negative 8h divided by x times x plus h, and then all times 1 over h. And those h's will cancel because you have one on top and one on bottom, and you are multiplying. So that's gone and that's gone. And so that's going to be equal to negative 8 over x times x plus h. And so that's the difference quotient of this function. Which again, the difference quotient is simply a generalization of this idea of average rate of change, which you'll see again, and you'll see this again in calculus. So let's take a look at number 6. And so in number 6, we want to use a graph of f of x to graph the function g of x equals, and in this one I changed this. This should be no longer there. So just negative f of x plus 1, and then all plus 3. So let's fix that real quick. So this should not even be there. Okay, so let's just do these transformations, and I can do it right on top of here. So the question becomes, which transformations do you apply first? The plus 1, the negative on the outside of the function, or the plus 3 on the outside? And of course, the order goes in which you would do if you plugged in a number. So if you plugged in a number, let's say 5, first you would add 1 to it. So what we want to do, since this is on the inside, you want to shift it not to the right, but to the left 1 unit. So I just take these points, and so this point is going to go right here to the left 1 unit. This point is going to go to the left 1 unit. This point will go to the left 1 unit. This point will go to the left 1 unit. And this point will go to the left 1 unit. And you can simply connect the dots now. And so this red graph is simply the graph of f of x plus 1. And then the negative on the outside, so what that's going to do is it's going to basically flip the outputs. If the outputs are positive, it'll make it negative, or if the outputs are negative, it'll make it a positive. So basically, it's just a reflection across the x-axis. So we can do this one in green. And so this red point will stay right here, but this red point will go up here. This red point will stay right there, but this red point will reflect down here. And then this red point will stay right there. And then we simply connect the dots the best we can with lines. All right, so the green one was negative f of x plus 1. And then finally, we're going to add 3. And since it's on the outside, these are outputs. And so you just basically add 3 to the output. So this green dot will go up 1, 2, 3. This green dot will go up 1, 2, and 3. This green dot up 1, 2, and 3. This green dot up 1, 1, 2, and 3. And finally, this green dot up 1, 2, and 3. And then you can connect those black dots, and we'll get our final answer then. And this black one, then that's our g of x, which was equal to negative f of x plus 1, all plus 3. Now you can even check your answer here if you want to. The way you can check your answer is you can just take x's and find out the outputs g of x. And so if you plug in 0, that's going to be g of 0, which is going to be equal to, you can plug it into the formula up here, negative f of 0 plus 1 plus 3, which is just equal to negative f of 1 plus 3. And you can read f of 1 off your graph. So f is this blue graph here. So if you go over 1 and go up 1. And so that's going to be equal to negative 1, because f of 1 is 1, plus 3, which equals 2. So is it true if you plug in 0, you get out 2 on the black graph? It is, and so I'm guessing it checks. So you can try other points too, but this is your graph of g. The next problem, number 7, involves the algebra of functions. And so you're given 2 functions, f and g. And first we want to find f times g of x. So remember, that's equal to f of x times g of x. And so that's just equal to 5x minus 2 times x plus 2. And you can do this multiplication, right? So this times this and this times that. So that's going to be equal to 5x squared plus 10x minus, because you have minus 2 times x, so minus 2x. So this times this and this times that, and so minus 4. And so my final answer when I combine like terms is 5x squared plus 8x minus 4. And then this one over here is not multiplication, it's composition. So remember, composition, you have functions inside of functions. So this will be f of g of x. And I just do what it says. So that's f of, and g of x is x plus 2. So I add an x plus 2 wherever I see a g of x. Then remember, f is a rule. The rule is whatever is here, you take 5 times it minus 2. So now this is the new thing that's on the inside. So I take 5 times it. So 5 times x plus 2. And then take away 2. And that's equal to, so distribute that 5 through. So you get 5x plus 10 minus 2, which equals 5x plus 8. Down here, we do f plus g of x. So that, we want to add 2 functions. So f plus g of x, what does that equal to? That's just equal to f of x plus g of x. And so that's equal to 5x minus 2 plus x plus 2. And then we just combine like terms. And so 5x plus x is 6x. And notice the 2's are going to cancel, so you just get 6x back. And we want to determine whether this function is even, odd, or neither. So there's several ways to do this. One, we could just make a table. So let's just make a table here, let's say, and you have x, and you have your output here, which is 6x. And if you look at negative 1, let's look at negative 1, 0, and 1. So you plug in negative 1, you get negative 6. You plug in 0, you get out 0. You plug in 1, you get out 6. So I think this might be an odd function, and you can even graph it. And if you graph it on your graphing calculator, you'll see that it looks something like, that's terrible. So you'll see that it looks something kind of like this, a line, and it has the same heights over here as over here, they're just the opposite. So this is an odd function. And then down here at part D, we want to find h of x, which is f divided by g of x. So h of x, which equals f divided by g, evaluated at x, which is just really shorthand notation for f of x over g of x. And that's actually very easy to find. You just put f on top and g on the bottom. And then we want to find its inverse. So remember, to find the inverse, you basically can write this as y equals 5x minus 2 over x plus 2. And what we'll do then is we'll swap out x's and y's and try to solve for y. So we'll rewrite this as x equals 5x or 5y minus 2 divided by y plus 2. And we'll solve this for y by multiplying both sides by y plus 2. And so on the left-hand side, what do we get? We get x times y plus 2 equal to, on the right-hand side, we have 5y minus 2 because the y plus 2's are going to cancel. We'll multiply through by x here and get what? We'll get xy plus 2x equal to 5y minus 2. And then we can get all the y stuff on one side by moving over the 5y and then moving over the 2x. So let's take away 5y from both sides. And we'll get xy plus 2x minus 5y equal to what? Equal to a negative 2. And then we'll take away 2x from both sides. And so when we do that, what happens is the 2x's cancel on the left, and you get xy minus 5y equal to negative 2 minus 2x on the right. Factor out that y, so you have y x minus 5, because we're trying to solve for y, and negative 2 minus 2x. And then divide out by the x minus 5 on both sides. And I get y equal to negative 2 minus 2x, all divided by x minus 5. And so you can leave it like that, or you can try to be a little bit fancy if you like, and write h inverse of x is equal to negative 2 minus 2x, all divided by x minus 5. You can check your answer by plugging in values over here. So, for example, I might plug in, h of 1. So h of 1 is equal to, you plug in 1 here, and you get 5 minus 2, which is 3, and you get 3 on the bottom, which is also 1. So that means if you plug in 1 down here, you better get out 1, otherwise I made a mistake. So let's try it. So when I plug in 1, I get negative 4 on top, I get negative 4 on the bottom, and negative 4 divided by negative 4 is positive 1, so it checks. So this, pretty good evidence that that's the right answer. All right, let's look at the last problem, number 8. We want to say on what intervals a function is continuous. And so it's actually pretty easy. You just trace the graph, and wherever you have to jump, you have a point of discontinuity. So this function is going to be continuous on negative infinity to positive 1. Union, and you can trace it up to here, up to input 3. So union 1 to 3. And then union, afterwards you're continuous, so 3 to infinity. So I am assuming that this function is going off in this direction, in this direction. So they're not arrows, but I'm assuming that's what's happening. Let's talk about limits. So now remember, for limits, what are we doing? So for limits, you're looking at the input value and saying as x gets closer to 4, so here's 4, what is the output doing? So if you look in the graph, this one's a nice and easy one. So as the inputs get closer to 4, you can see it's a nice point on my graph, and so the outputs are getting closer to 4 on either side. On the next one, we're going from the left and the right. So here's 1 from the left. That's what that negative in the exponent means. So 1 from the left. You can see it's coming down and approaching height 4, so that's equal to 4. Right? So that's when you come in from the left of 1. And then when you come in from the right of 1, right? So if you come in from the right of 1, oh, you look on the graph and it's also coming down to height 4. And so that's what that plus sign means, the exponent coming in from the right of 1. And then, of course, as you go to 1, since the limit from the left and the limit from the right are exactly the same, we say this is equal to 4. Now this one's just evaluating the function at a point. So f of 1 is equal to what? Well, when you plug in 1, you get out the number 5. So this is an example where the limit exists, but it's not equal to the actual value. The next example, what's happening, we want to take a look at the limit as we go to 3 from the right. So over here, here's 3 when it coming from the right-hand side. So we come down from the graph and we approach height 3. So that's equal to 3. Versus the limit from the left of 3. So look, you can come in from the left of 3. So you go up on the graph and look and say, oh, from the left, it has height 6. Now, since the left-hand and the right-hand limits are not the same, right? The left-hand limit is 6, the right-hand limit is 3. We say this one, DNE, does not exist. And f of 3, that's the actual value. That's what the closed circle is. F of 3 is actually equal to 4. And that's it.